Today's topic is electromagnetic waves parallel to B0. Consider electromagnetic wave propagating parallel to the direction of magnetic field B0 vector. Let propagation is along the direction of z-axis. Then we have k vector equal to kz cap. K vector is propagation vector. It represents the direction of propagation. So we assume that electromagnetic wave is propagating along the direction of z axis. So k vector is equal to k z cap. And we are considering the case when electromagnetic waves which is parallel to B0 vector. So B0 vector is also along the direction of z-axis. So B0 vector is equal to B0 z cap. So k vector and B0 vector are parallel to each other. Both are along the direction of z-axis. Z cap is unit vector along the direction of z-axis. Let electric field is in xy plane and we write E1 vector equal to Ex x cap plus Ey y cap. Maxwell's equations are Maxwell's third and fourth equations are for curl E and curl B. These equations are del cross E1 equal to minus B1 dot and C square del cross B1 equal to J1 upon epsilon 0 plus E1 dot. These are Maxwell's third and fourth equations. We write these two equations as equation 1 and 2. The time derivative of second equation is given as C square del vector cross B1 dot vector. If we take time derivative, then B1 vector change to B1 dot vector, and in right hand side J1 vector changes to J1 dot vector and E1 dot vector changes to E1 double dot. E1 dot is differentiation with respect to time t. Double dot is 2 times differentiation with respect to t. So if we differentiate with respect to t, second equation becomes C square del vector cross B1 dot vector equal to J1 dot vector upon epsilon 0 plus E1 double dot vector. Taking the curl of equation 1, if we take the curl of equation 1, put del vector cross before left hand side and right hand side, we get del vector cross E1 equal to minus del vector cross B1 dot. Del vector cross, it is curl. So taking the curl of equation 1, we write del vector cross before the left hand side and right hand side of this equation 1. So we get this relation del cross E1 equal to minus del cross B1 dot. Now left hand side can be solved by using the relation A vector cross B vector cross C vector equal to A dot C times B minus A dot B times C. So A dot C will give del vector dot E1 vector and times B means times del vector. This del vector we write before del dot E. And then we have minus A vector dot B vector times C vector A vector dot B vector is del vector dot del vector, it is del square. So we have del square E1 vector. And in right hand side, we put the value of del cross B1 dot from this relation equation 3. We put the value of del cross B1 dot and get in right hand side as minus J1 dot upon C square epsilon 0 minus E1 double dot upon C square. Assuming plane wave solution, assuming that plane wave varying as e to the power I k vector dot r vector minus omega t, then we have for del vector we have I k vector, and for delta upon delta t we have minus I omega. If we differentiate with respect to t, we will get the term with t in exponential, and it is minus I omega. With t we have minus I omega. So delta upon delta t is equal to minus I omega, and for del vector, which contains the derivatives with respect to x, y and z, we get for del vector the term with r vector, and with r vector we have I k vector. So del vector is equal to I k vector, and delta upon delta t is minus I omega. If we use these relations for del vector and delta upon delta t, then above equation becomes minus k vector times k vector dot E1 vector. Here we write I k vector for del vector, and I square becomes minus 1. In second term also we put I k for del vector, it is del square, so it is I k into I k, so it is I square k square, which is minus k square. So second term becomes plus k square E1 vector, and in right hand side this J1 dot, it is the differentiation with respect to t, it is delta J1 upon delta t. Delta upon delta t is minus I omega, so it becomes I omega J1 upon C square epsilon 0. Similarly, in the second term of right hand side we have E1 double dot. Double dot is 2 times differentiation. 1 times differentiation delta upon delta t is equal to minus I omega. So 2 times differentiation will be equal to minus I omega into minus I omega, that is I square omega square, and it is minus omega square. So E1 double dot becomes minus omega square E1. Now k vector dot E1 vector is equal to 0. It is transverse wave. K vector is along the direction of z axis, and E1 vector is in xy plane. So these two vectors are perpendicular to each other. So this dot product is 0. K vector dot E1 vector is 0. So the first term in left hand side is 0. And we have k square E1 equal to I omega J1 upon C square epsilon 0 plus omega square upon C square E1. Take the term of E1 in left hand side, then we have omega square upon C square E1 minus k square E1 equal to minus I omega J1 upon C square epsilon 0. And for J1 we write minus N0 E V E1. J1 is current density. It is current density due to electrons. So current density due to electrons is written as minus NeV. Minus E is charge on electron. For N we write N0. It is the number of electrons per unit volume, and VE1 is velocity of electron. E1 is taken common in left hand side. Multiply by C square the entire term. So C square in denominator is cancelled out, and we have omega square minus C square K square into E1 equal to I omega N0 E VE1 upon epsilon 0, multiplying by C square. As E1 vector is Ex x cap plus Ey y cap, from the linearized equation of motion of electron, we have, this is the equation of motion for electrons. In left hand side we have mass into acceleration, that is force. Acceleration is delta V upon delta T. And for V we have VE1, it is the velocity of electron. So mass into acceleration, mass into delta V upon delta T equal to force, and force on electron due to electric field and magnetic field is minus E into E1 plus VE1 cross B0 vector. For delta upon delta T we write minus I omega, so left hand side become minus I omega into M VE1, and in right hand side we have minus E into E1 plus VE1 vector cross B0 vector. From this we have VE1 vector divide by minus I omega M. So we get VE1 vector equal to minus IE upon M omega into E1 vector plus VE1 vector cross B0 vector. VE1 vector, we write it as Vx x cap plus Vy y cap plus Vz z cap. Let its three components are Vx, Vy and Vz. And in right hand side we have minus IE upon M omega. E1 vector is Ex x cap plus Ey y cap. And we can find this cross product VE1 vector cross B0 vector by solving the determinant, having first row as I x cap, y cap, z cap, having second row as Vx, Vy, Vz, which are the three components of VE1 vector, and in third row we have components as 0, 0, B0, because B0 vector is B0 z cap, it is along the direction of z axis. And by solving this determinant we can find the value of this cross product VE1 vector cross B0 vector, and it comes out to be Vy B0 x cap minus Vx B0 y cap. Now we can find the values of Vx and Vy by comparing the coefficients of x cap and y cap in left hand side and in right hand side. Now if we put the value of Vy from lower equation to upper equation, these two equations we write equations 5 and 6. Equation 6 is for Vy, and put this value of Vy in equation 5. We get Vx equal to minus IE upon M omega into Ex minus IE upon M omega into Ey minus Vx B0 into B0. Here we put the value of Vy from this equation 6 into equation 5. to find the value of Vx. So it becomes E upon m omega minus I is taken inside, and the second term then becomes minus E B0 upon m omega into Ey minus Vx B0, and it is equal to E upon m omega into minus I Ex minus this term E B0 upon m. It is omega c. It is electron cyclotron frequency E B0 upon m. In the second term, inside the bracket in right hand side, this term E B0 upon m is equal to omega c. So we write it as omega c. Omega c is electron cyclotron frequency E B0 upon m. Now Vx becomes equal to E upon m omega into minus I Ex minus omega c upon omega Ey plus omega c upon omega Vx B0. Take the terms of Vx into to left hand side. There are two terms of Vx. Put them in left hand side and take Vx as common. If Vx is taken as common, we have Vx into 1 minus omega c square upon omega square. Again here the term appears as E B0 upon m, and we write it as omega c, electron cyclotron frequency, and it is equal to E upon m omega into minus I Ex minus omega c upon omega Ey. So we can find the value of Vx by dividing by 1 minus omega c square upon omega square. So Vx now becomes E upon m omega into minus I Ex minus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. In a similar manner, we can find the value of Vy, and it is Vy equal to E upon m omega into minus I Ey plus omega c upon omega Ex into 1 minus omega c square upon omega square to the power minus 1. So these are the two values for Vx and Vy. We write these as equation 7 and equation 8. If we find the value of Vx, we can write the value of Vy by replacing Ex by Ey, replace Ex by Ey, and replace Ey by minus Ex. So we can find the value of Vy similar to the value of Vx. Change Ex to Ey and change Ey to minus Ex. Other terms are same. So these are the two values of Vx and Vy. Separating equation 4 into x and y components using equations 7 and 8. This is equation 4. Write it in terms of its components. E1 vector is Ex x cap plus Ey y cap, and Ve1 vector is Vx x cap plus Vy y cap plus Vz z cap, and values of Vx and Vy are given by these two equations, equations 7 and 8. Then x component of this equation becomes omega square minus c square k square into Ex equal to I omega n0 E Vx upon epsilon 0, and put the value of Vx from this equation 7. So omega square minus c square k square Ex will becomes equal to minus I n0 E square upon m epsilon 0 into I Ex plus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. n0 E square upon m epsilon 0. The term outside this bracket in right hand side, the term with minus I is n0 E square upon m epsilon 0 and it is omega p square. It is electron plasma frequency, square of the electron plasma frequency, omega p square. So right hand side becomes minus I omega p square into I Ex plus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. It is equal to omega p square upon 1 minus omega c square upon omega square into Ex minus I omega c upon omega Ey multiplied this minus I is taken inside the bracket and we write it as alpha into Ex minus I omega c upon omega Ey. We write alpha for omega p square upon 1 minus omega c square upon omega square. Take the terms of Ex to left hand side. Then we have with Ex omega square minus c square k square minus alpha multiplied by Ex. Take all the terms to the left hand side. So the term with Ex is this omega square minus c square k square minus alpha multiplied by Ex, and the second term is plus I alpha omega c upon omega Ey equal to 0. So we have two terms, one of Ex and second of Ey. Similarly, we can find the other equation from y components, and it is omega square minus c square k square minus alpha into Ey. Ex is changed to Ey, and then we have minus I alpha omega c upon omega Ex. Here Ey is changed to minus Ex equal to 0. Write it in this way. The term of Ex we write, first we write the term of Ex and then second we write term of Ey. Now we have these two equations having two terms, first the term of Ex, second the term of Ey. Setting the determinant of coefficient of Ex and Ey equal to 0, we have, for non-trivial solution, this is the condition that the determinant of coefficients of Ex and Ey must be 0. So put the determinant of coefficients of Ex and Ey and write it equal to 0. This will give this relation omega square minus c square k square minus alpha whole square equal to alpha omega c upon omega whole square. Take under root. This will give omega square minus c square k square minus alpha equal to plus minus alpha omega c upon omega, or omega square minus c square k square becomes equal to alpha into 1 plus minus omega c upon omega. Now put the value of alpha. We assumed alpha as omega p square upon 1 minus omega c square upon omega square. So write the value of alpha, which is omega p square upon 1 minus omega c square upon omega square, and we have into 1 plus minus omega c upon omega. Now it will become omega p square into 1 plus minus omega c upon omega divided by 1 plus omega c upon omega into 1 minus omega c upon omega. Denominator is written as 1 plus omega c upon omega into 1 minus omega c upon omega. So this will becomes equal to omega p square upon 1 minus plus omega c upon omega. If we take the plus sign in numerator, then 1 plus omega c upon omega is cancelled out, and in denominator we have 1 minus omega c upon omega. And if we have negative sign in numerator, then 1 minus omega c upon omega is cancelled out, and in denominator we have 1 plus omega c upon omega. So we have omega square minus c square k square equal to omega p square upon 1 minus plus omega c upon omega. Now dividing by omega square, this entire equation divided by omega square, we get 1 minus c square k square upon omega square equal to omega p square upon omega square upon 1 minus plus omega c upon omega, or c square k square upon omega square will be equal to 1 minus omega p square upon omega square divided by 1 minus plus omega c upon omega. The minus plus sign indicates that there are two possible solutions of equations 9 and 10. So we have two different waves that can propagate along P0. The dispersion relations are c square k square upon omega square. It is c square upon v square, because v square is omega square upon k square. V is omega upon k. It is Vp. Vp is omega upon k. So c square upon v square, it is n square. N is refractive index. And refractive index is defined as c upon v. So n square equal to c square upon v square. That is c square k square upon omega square. So the term in left hand side is c square k square upon omega square. It is n square. N is refractive index. And we have two values for n square, one with negative sign and one with positive sign. The term with negative sign is given by this equation 11, and we call it as R wave. And the term with positive sign is given by equation 12, and we write it as L wave. So these two types of waves, R wave and L waves, can propagate when electromagnetic wave is along the direction of B0 vector. The R and L waves are circularly polarized. R wave is right hand circularly polarized, and L wave is left hand circularly polarized. The electric field vector for R wave rotates clockwise in time as viewed along the direction of B0 vector, and vice versa for the L wave. These two waves are shown in this diagram. R waves and L waves, these are circularly polarized. This diagram shows B0 vector is along the direction of Z axis. E vector is in XY plane. Wave is propagating along the direction of Z axis. K vector is along the direction of Z axis, and B0 vector is also along the direction of Z axis. E vector lies in XY plane. It has two components. Ex and Ey. So it lies in xy plane, and the head of E vector rotates clockwise for R wave, which we write by ER. It is right hand circularly polarized. Head of its E vector rotate clockwise, and for L wave this EL vector rotates anti-clockwise. So these are right circularly polarized and left circularly polarized waves, R waves and L waves. R waves, for R waves it is right hand circularly polarized. Its head of E vector rotate clockwise. Rotate clockwise when we see along the direction of B0 vector, along the direction of Z axis. If we see along the direction of Z axis, then this head of E vector of R wave will rotate clockwise, and it rotates anti-clockwise for L wave. Following figure shows the dispersion curve Vp square upon c square, which is omega square upon c square k square. These are the equations for c square k square upon omega square. It is n square, and the graph is plotted for Vp square upon c square. It is inverse of this. It is c square upon Vp square, left hand side. N square is equal to c square upon Vp square, and the graph is plotted between Vp square upon c square versus omega. These two waves are shown here, R wave and L wave. R wave are shown by dark lines, and L wave is shown by dotted lines. We see that for R wave, Vp square upon c square is positive for omega when omega is between 0 to omega c. Vp square upon c square is positive, and it is also positive when omega is greater than omega r. So these are the two regions of propagation for R wave when Vp square upon c square is positive. And similarly for L wave, Vp square upon c square is positive when omega is greater than omega L. So this is the region of propagation for L wave. Following figure shows the dispersion curve Vp square upon c square, which is omega square upon c square k square versus omega curve. The regions of non-propagation are for which omega square upon k square is negative, and the regions of propagation are for which omega square upon k square is positive. These are different for two waves. Regions of propagations for two waves, L wave and R wave, are different. Regions of propagations are those for which Vp square upon c square, which is omega square upon c square k square, is positive, and regions of non-propagations are those for which Vp square upon c square is negative. So these two regions are different for these two waves, L wave and R wave, and these are shown in this figure.